Okay, so welcome back. Today we're going to talk about rearrangement of terms. So there are some cases where we are able to rearrange terms of a series. And so you might be thinking, well, why would we do that? Well, it turns out that in a finite series, obviously you can rearrange terms of a finite series, and the rearrangement of the terms will not change the end resulting sum. And you're thinking, that makes sense, right? Okay. Now, when you're talking about infinite sums though, infinite series, things get a little more interesting. Okay? For example, if I take the alternating harmonic series here, we know that this converges, and it converges conditionally. So if I take the absolute value of this, we get the harmonic series which diverges. Now, the interesting thing, there's a relationship between absolute convergence and conditionally convergence that also corresponds to whether a rearrangement of the terms will give you a different answer or not. So here's the thing. There are ways where when you're dealing with infinite series, you can rearrange the terms to make the sum either diverge or converge to any value you want. And you might be thinking, like, how in the world does that happen? Well, I'm going to show you an example of how that works. For example, you can use this on the harmonic series. So I can rearrange the terms and get the harmonic series to equal anything. Now we know the alternating harmonic series, that's what I'm referring to, the alternating harmonic series. We know that this converges to the natural log of 2. Okay? But we can make it converge to anything. Okay, not just that. Or we can make it diverge. So why is this important? Why does it happen? Well, again, it has to deal with the fact that we're dealing with infinities, infinite sums. And when you're dealing with things that deal with infinity, well, some things you can get away with. Okay? Things that happen in mathematics with infinity, which works, but doesn't make sense in the real world, right? It doesn't make sense in the physical world. For example, look up the Hilbert's Hotel. That's a great example of how infinity works in mathematics, but doesn't quite work in the real world. And there's a famous mathematician by David Hilbert who kind of came up with this example called Hilbert's Hotel. Okay, that has an infinite number of rooms with no vacancies. So look it up. But it's interesting. It's pretty cool. But anyway, okay, so if we look at the alternating series, the thing is now again, I'm explaining things that are beyond the scope of this class, so I'm not going to get into proofs. I'm not even going to go in and I'm going to do one example of how this works, but I'm not going to prove it because, again, it's beyond the scope of this class. It's actually based on Riemann, it's called the Riemann rearrangement theorem. Again, beyond the scope of this class. But here's what you need to know. This is the takeaway. It turns out that if a series is conditionally convergent, okay, or if it exhibits conditional convergence, in other words, that you can rearrange the terms of that sequence and you can get it to converge or diverge or converge to any number you want. But if the series converges absolutely or exhibits absolute convergence, then it doesn't matter what the rearrangement is. Any and all rearrangements will give you the same sum. Okay, so that's the takeaway. Okay, so what I'm going to do is I'm going to do an example of showing you how I can make this series, the alternating harmonic series, equal something other than the natural log of 2. So I'll do that next time.